All right. Hello there. My name is Agustin Ciciliani, and today we're going to cover single area OSPF, a deep dive. This is the first of a series of videos about CCNA technologies, and the idea is to explain them to you in a different approach so you get some more ideas and some more understanding about these subjects. I'm with Firefly, and our vision is changing the way we learn, evaluate, and adopt technology. Okay, so this is the agenda for our video today. We're going to first discuss a little bit about why link state, why that name for the protocol, some history and background about that. Then we're going to touch base on an overview of two computer science theory topics. One is state machines, the other one is graphs. Hold it there. This may not make sense at the beginning. Hopefully, it will on our next section where we put everything together. And finally, we are going to analyze a capture from a lab we've made so you see how this works in real life. Okay, so on our first topic, we discuss why we say OSPF is a link state protocol. Can it take other names? Well, we begin checking out RFC 2328. By the way, if you never heard of RFCs, these are documents that the IETF puts together. IETF is the Internet Engineering Task Force. So basically, these guys gather together, discuss how the protocols are going to work, and they write that down on these documents called RFCs. So for OSPF, we see in the introduction section that there is a small history part where it mentions that OSPF was based on an old protocol running on the ARPANET. If you remember, the ARPANET was the old Department of Defense network in the US. And very interestingly, this protocol says that it maintained a database describing the complete network topology, and it can also understand the delays, so it has information about the delays of the lines connecting those nodes. So going forward, we do have some other names for OSPF. It is also known as SPF-based protocol. We're going to see what SPF is in a few later on. And it's also called a distributed database protocol, which is pretty similar to what the old ARPANET protocol was. So this first link state routing protocol running on the ARPANET was able to understand the delays of the links connecting each of the nodes and was able to make routing decisions based on the delays of the links. So basically, if I have two different paths and path one has more delay than path two, I would prefer path two, right? Because it has smaller delay, and I want my message to go across faster. So although this is not really a capability of OSPF, it inherit that name right from this old protocol, which was able to detect the delay at that moment on the leased lines or the synchronous lines that were connecting the old Department of Defense. So finally, these as part of the RFC, as part of all these OSPF capabilities, this was extended to not only work on lines, but also work on our well-known Ethernet broadcast networks. So that's why they added or they extended the protocol to support multicast, to support areas, and to support these DR or BDR concepts that you may heard of them, and basically to operate more efficiently on TCP/IP networks. Okay, so we continue this section with our first weird topic, which is the state machines. So why do we need to learn about state machines? Okay, hold it there. Hopefully it's gonna make sense later. But by the way, there's this great blog by Mark Shedd. If you wanna take a look here, this is the link where it is gonna explain with much more detail what a state machine is and how it works. I'm gonna do it as simple as possible. You're doing some whiteboard guys for you. So let me create a simple drawing here. Let's suppose I have a couple of boxes, or this could also be circles when we draw these kind of things. Then let's suppose I have here an arrow like this. I can have another arrow like this, right? connecting them. Let's suppose I have here, it's going to be a little bit thick, but never mind. This is another arrow, like pointing to itself, another arrow like this. And I'm going to say that this is going to be a reference, right? That these boxes are going to be states. States, right? So each box represents a state. And I'm going to say that the arrows are going to be events. So the arrows represent events like this. So let's suppose I have two different states, right? Let's suppose I have a happy state, and let's suppose I have here a sad state. Okay. So let's suppose I receive an event, which is basically somebody saying to me goodbye, goodbye. So I'm gonna be sad. And let's suppose I receive a hello message. Sorry, let's suppose I receive here a hello message. So I'm gonna be happy, right? And if my state remains here, if I keep receiving hellos like hi's, hello, I'm gonna keep staying happy. But if I'm still receiving goodbyes, I'm gonna be sad, right? So goodbye here, goodbye. So basically, this is my state machine, right? So I have two states, happy and sad, and depending on the events, right, that I'm reading or that I'm getting or that I'm sensing, my machine is gonna change or not from one state to the other. Okay, hopefully this makes sense. So you understand this is again basics of computer science. So basically, this shows how a state machine, as it's called, can work. And basically what guys you have to take from here is that the state machine basically has states and events, right? And depending on those events, my machine can change from one state to the other or stay on the same state. Okay, so this is our second weird topic that we're gonna see here to see, and hopefully it's gonna make sense for OSPF as well. So basically, we're gonna discuss about graphs. So graphs are basically graphical representations of relationships. So basically, we represent usually a node by a dot or a circle here. Basically, a node is an item or an entity, right, that somehow relates to other entities of the same kind. And the edges, right, are the links or the situations that bond them together, right, that links those two nodes. So again, node and edges. So that's the basics of graph theory. If you're going to check more also, this is just a very brief overview. You can check that this stands for link, which is it has a better explanation and more detailed explanation. But basically, what we can do with graphs, basically, we can, for instance, represent chemical relationships. We can represent streets and corners, right? Which is each node, it could be a corner, and each street is going to be the edge. People relationships, for instance, in LinkedIn, we could represent the LinkedIn network, right, using a graph. That's why we care for OSPF, because we can represent a network topology using graph theory, right? Where every node is basically a router, and every edge is going to be a link connecting those two routers. Okay, guys. Next topic. I promise this is the last one that seems to be that has nothing to do with OSPF. If you remember at the beginning, we said that OSPF is an SPF protocol, and I'm sure you have heard that OSPF runs the Dijkstra algorithm, right, or the SPF, the shortest path algorithm under the hood. So what's that? So basically, Dijkstra is actually the last name of the computer scientist that created the SPF algorithm. The fun story is that this guy looks like he was tired after doing some shopping in Amsterdam with his fiancée, and he sat down, he had a coffee, and he was thinking, what was the shortest path or shortest way to travel from Rotterdam to Groningen? I'm sorry, see, I'm not pronouncing this correctly. And at that time, of course, we didn't have Google Maps or things like that. So he created in a sheet of paper the SP algorithm, and that was part of nowadays the computer science protocol. Computer science protocol. So very nice. And if you see, this is so simple that although this may maybe look difficult at the beginning, it's not. It's a very simple computer program, a computer function actually, that can easily be written in Python, for instance, and it shows right in a very a small amount of lines how the SPF algorithm can be programmed. So how this works? Let's suppose I have here a network, right, or a graph, which is basically a graph where I have the nodes here in blue, and I have here the links or the edges, right, in black, and the cost, right, the 3, 7, the 5, the 1. These are the costs to reach from one node to the other. So how this works, this function first, what it does, let's suppose I'm starting from point A and I want to calculate the distance, the best distance or the shortest path to B. What the algorithm is going to do, it's going to step on, first of all, on in this case A, right? It's going to say that the distance to the source where I'm starting the graph is going to be 0, and it's going to say that the distance to each of the rest of the nodes at the beginning is going to be infinite, right? So that's what it does, this first for loop here. Then we have here the main loop, right? This main while loop that is basically is going to take a queue. So first of all, I put all the nodes in a queue, and it's going to start dequeuing each of the nodes, and it's going to start calculating for each node the cost to each of the neighbors and the rest of the nodes, right? So basically that's what it does, right? So it says, okay, I take the first node from the queue, I calculate the minimum distance, and then I go to the next in the queue. And for each of the neighbors, I'm going to say if the distance is better than the distance I had previously. If you remember, if I started with infinite, of course, the first run is always going to be better. I'm going to start putting the best distance I'm calculating on each of the loops, right? So basically, that's what it's doing, right? It's going through each and every node, it's going through each and every neighbor from one source to the other, then passing through each of the nodes and calculating the best path, right, to reach from every point to any other, right, taking into account the different path and different costs.